Hey everybody, and welcome to another Jamovi tutorial. In this tutorial, I'm going to be talking about a new module added very recently to Jamovi, and it's called the Brunner-Munzel test. And it was created, Brunner-Munzel, for some reason I can't highlight on this, and it was made by Karch. So this is his 2021 APS, Advances in Methods and Practice in Psych Science paper, where he argues that the Brunner-Munzel test should be used instead of a Mann-Whitney U test if you need non-parametric tests. And he says, exchangeability is the reason, right? Exchangeability is the reason. And he explains here why that is the case, okay? And he says, even a t-test might be a bad idea, especially if you have ordinal data or data that was created to look like no improvement, substantial, slight improvement, substantial, symptom-free, right? So these are labels that don't really have set intervals in between them, right? We don't know what no improvement or slight improvement to substantial improvement means. We don't know what substantial improvement to symptom-free means, right? So imagine you're talking about a control treatment thing on depression, right? After 12 months of therapy. So if you code 1, 2, 3, and 4, you end up with a t-test using the Welch bias correction of 0. And of course, the probability of that is astronomical, almost 1, right? So null test, get rid of it. There was no help. But if you code no improvement to 0, but leave 2, 3, and 4 as your codes for the other labels after 12 months, then you get a significant Welch's t-test. And that presents a problem with that. And really what we're looking at is a 0.05 change when we calculate values here. And the only reason why this 0.05 change between the control group and the treatment group is because we have 10,000 participants. 10,000 participants. So Karch in this article argues that you should use the Brunner-Munzel test. Okay, well, in 2023, published a paper that suggested that, well, if I want people to use the Brunner-Menzel test, I better make a package for it because it's not available in proprietary packages like SPSS. So he made an R module and then he wrapped it for Jamovi, and that's what we're going to look at today. So let's pull up Jamovi here. So to find Jamovi, you go click on module. To find it in Jamovi, you go on to click on modules and you go to installed or available, depending on what you have. You would go to available, of course, and then you would type in BM test and it'll bring up the Brunner-Munzel, and you can see that the author here is Karch, as we've said. You can read more about how this module works in his 2023 paper, which I just showed you right here. And it's free and open source. It's available to download wherever you are. The Brunner-Munzel test provides a more robust version of the popular Wilcoxon-Mann-Whitney test. It is recommended to almost always use the Brunner-Munzel test, and he specifically suggests that this should be used even in place of t-tests, and I'll show you why on one of the learning statistics with Jamovi tests. The tests in the module are described in detail in Karch, okay? So let's go ahead and close that and open up BM test, Brunner-Munzel test. So we're gonna open that. I did the same exact thing that I did. We gotta open the data, and so I'm in the data library, and then I'm in the LSJ-data. You can add these data sets using the modules. You can just type in LSJ, and it'll bring that one right up. I'm gonna go ahead and open the Harpo chapters 11 and 15 student grade in Dr. Harpo's class. It's gonna open up a new window, and I should have remembered that it does that. It's been a while since I've been in JASP. So here we have our ID, our grade. I'm going to change this to a continuous variable. Jamovi does that thing where it thinks all whole numbers are whole numbers, for example. And then we have different tutors. And so what we're trying to test is the hypothesis that Anastasia is a different type of tutor than Bernadette, and their scores of these 33 students are going to reflect that. So let me run the BM test, and then I'll show you how that compares to the Welch's, to the independent samples t-test that you get over here in the base Jamovi. So let's do the Brunner-Menzel test. We're going to go ahead and put tutor, Bernadette, or Anastasia, and then we're going to put grade in the dependent variables here. Okay, so before I change anything, I want to point out what it is that we are attempting to find here, okay? So it's a little bit easier to read in the paper, so I'm going to go ahead and open that. I'm going to scroll all the way down to where it is. Okay, so the p-value that we get here is based on the following probability statement. Okay, because we're comparing two things, what we are going to do is we are going to check a relative test of 0.5 or 1/2. Okay, so the idea here is that 0.5 is basically, if you're doing a binomial test, 0.5 is if they are equal, if the null hypothesis is true, then the probability here from this equation should be 0.5. Okay, so if they're statistically comparable, as he said, or stochastically comparable, I should say, then this value should be 0.5. So that's our null hypothesis. And so you can see here that we are attempting to do a not equal. We don't know what direction. We don't know if Anastasia or if Bernadette is a better tutor. So we're saying, you know what? That's not going to equal 0.5. And so what we're doing is we're saying the probability that Anastasia is worse than the mean of that, basically, is worse than the mean of Bernadette scores. And then we're adding half the probability that they are equal to each other. So we're going to split that probability. Okay. So that's what this note is for, right? So we have the probability that Anastasia is less than Bernadette plus 1/2 the probability that they equal each other. But then that whole thing does not equal 0.5. So what's the probability of that? And that is what we get right here, 0.5. We can also add to this table the relative effect and its confidence interval. And what you see here is that this expression is actually equal to 0.294. So that's suggesting that Anastasia is better than Bernadette, okay? Because we haven't reached the relative 0.5 of the two being equal. Anastasia is going to be better. And we don't have descriptive statistics here, but I'm going to bring up the t-test here, the independent samples t-test, to show you. And then our confidence interval does not include 0, so we're pretty good here. And that leads to a statistic of negative 0.205, okay? Because Anastasia comes first and Bernadette comes second, this negative value is telling us that Anastasia is better than Bernadette. How do I know that? Well, I'll show you in just a second. We have degrees of freedom of 19.1. That is not n-1, as you know, because n-1 plus n1 minus 1 plus n2 minus 2, or n-2, because that would be a degrees of freedom of 31. This is an adjusted degrees of freedom value. And these two things combine on a known distribution to tell us what a probability value is. But oh boy, that is 0.054. You're left with the, rounding. Do I truncate or do I not truncate? Well, let's be a little bit more conservative and take the value at face value, right? 0.054 tells you that the probability is actually greater than 0.05, right? So if we were taking the literal definition of our criterion, our alpha of 0.05, then we have to fail to reject. We fail to reject the null hypothesis. But let me go ahead and run the t-test to show you why this is borderline, and you should, unfortunately, for alternative hypotheses, err on the side of conservative caution and choose the Brunner-Munzel test. So let's go ahead and put grade over here and tutor over here, and let me grab the descriptives just to show you why the negative value tells me that Anastasia is better than Bernadette. Okay, so this says Anastasia is less than Bernadette, but Anastasia is technically greater than Bernadette, right? 74.5 to 69.1, so about a 5-point difference on their tests collectively. But those are really close. 5-point difference on a 100-point test, that's a 5% margin of error, and we only have 33 participants, 15 and 18 per group, respectively. So 5% is really small when it comes down to the variability that is present in both of these groups. And with the independent samples t-test, we end up with a p-value of 0.043. That is less than 0.05, and if we were just going to run the t-test, we run the risk of saying that there is an effect, that Anastasia is better than Bernadette, full stop, when we really don't have that information. That evidence isn't presented, right? Because of this exchangeability assumption, there could be so many things that Anastasia and Bernadette do differently that we don't know about, that we couldn't possibly. And so the idea with the Brunner-Munzel test is to run this first, see what that p-value says, and then maybe run an independent samples t-test to see what the differences are. But according to Karch, you should run with this if you were going to try to publish a paper with an independent samples design, so that you should do this as opposed to anything else. So you can be a little bit more conservative, a little bit more cautious in saying that one group is different from the other, your treatment's different from the control. And in this case, we can say that Anastasia's slightly better than Bernadette, but there's not enough information, and the sample sizes are really small, and that's what's going to happen with this, right? T-tests are very sensitive to sample size changes. Now you can do random permutations, you can do full permutations of this in the Brunner-Munzel test, although the full permutation is giving not a number of needed permutations too large to be computationally feasible. Use one of the other two options. So full permutation, there are too many. The computer just says, nah, I'm not going to do it. Now the random permutation gives us the same statistic, almost exactly the same p-value and the same probability value for the Brunner-Munzel test estimate. So, and then very similar confidence intervals there. You can change your alternative hypothesis to one group is better than the other or bigger than the other, and then you can deal with missing cases similar to independent samples t-tests. And that's the Brunner-Munzel test. If you have any comments, suggestions, questions, or other feedback, please leave those down below. Thanks so much for watching this video. I'll see you in the next one. Bye.